So I'm going to go ahead and get started. Thank you, Sam, so much for the introduction. So you all were promised a hands-on demo with Splice Machine, and that we are going to deliver. But first, we're going to start with some slides just to explain what is Splice Machine, what are we going to talk about in the demonstration today, and what you guys are going to be doing. So the first question is, what is Splice Machine? Splice Machine, first and foremost, is a single hybrid database. It performs both analytic and transactional queries. In this conference, we are focusing on a particular use case of that database, being the machine learning platform and the feature store. Splice Machine is entirely Kubernetes orchestrated. It works on any cloud, it works on premises. You can sort of pick it up and move it wherever you want to use it. You're not constrained to a single cloud. Splice Machine is also scale out. You can add more nodes, add more Spark executors as necessary, and execute queries on data of any size. And finally, Splice Machine is modular. The first piece and the critical component is the hybrid database. There's, of course, also the feature store and the ML platform, which I'm going to show you today. Your organization does not have to use every piece of this platform. If any part of it is of interest to you, you're more than welcome to use just that part. However, what we're going to show you today is using the whole package, using the feature store and the ML platform in conjunction, because we think that that has added benefits, added synergies using the whole package. So what powers Splice Machine? What is this hybrid database? Splice Machine has the key component of Splice Machine is this cost-based optimizer. When you write any SQL query, this cost-based optimizer will take a look at that SQL query and send it to the appropriate engine depending on the type of query that it is. If it's a primary key lookup, it'll send that to OLTP execution done through HBase. And if it's a big aggregation with multiple joins and group by clauses, it'll send that to the OLAP execution, which is powered by Spark. What this means is that Splice Machine can do really any type of workload, and the user doesn't have to send data to the appropriate database or understand the underlying execution path. The optimizer takes care of that for you. So that is what powers Splice Machine. A common question we get asked is, how can this hybrid model support both types of applications? How can you ensure various SLAs? How can you ensure that the whole system is operational and functional at scale at enterprise speed? And the reason is because the OLTP engine and the OLAP engine are given isolated resources. You can scale them independently. So if a big job is running on the OLAP side, a big group by execution done by some data scientists, for example, that in no way affects the real-time OLTP side of the database. They have independent resources. The other benefit of this system is that these can be scaled independently and very easily, just with a sliding resize bar like this. So if your organization, for example, is at this time really focused on batch analytic queries, you are maybe just dipping your toes into the real-time OLTP side, that's great. You can really scale out this OLAP side of the database, keep this OLTP side small, and control your costs in that manner. Of course, you could do the reverse or have something of a balance. So because these resources are independent, you don't have to be concerned with one type of query affecting the performance of another. So as I mentioned before, we're going to talk today about two use cases for this database. The first is the feature store. What is a feature store? At this conference, there's been a fair bit of discussion about a feature store. It allows you to serve features for inference, and it allows you to create training sets in a point-in-time consistent manner, typically done through two databases. So overall, we see four key benefits, the two I just mentioned, training sets and feature serving. And then you also oftentimes have the ability to search for features through some kind of search bar, which is something I'm going to demonstrate today. And it also offers oftentimes some kind of data governance consistency. You get an end-to-end story of what the data has looked like throughout the process. So feature stores do these four incredible things, and that's wonderful for many organizations. But like many things, if it sounds too good to be true, it sometimes is. In exchange for these four benefits, most feature stores come with a cost, and that cost is data inconsistency between your two databases. When a two-engine feature store, your typical feature store, is operating perfectly at 100% capacity exactly the way it is designed, there is going to be latency between your two databases, between your online and your offline database. And that's in the best case scenario. There's going to be a disconnect of some kind, some amount of data parity issues between the two. Now, in the real world, in a real business setting, issues arise from time to time. And two-engine feature stores can really struggle if there is a disconnect between that online and that offline engine. You could imagine that a data scientist adds a feature to the offline engine, but not to the online engine, or vice versa. And then there's a gap between these two databases. There's a parity issue. Additionally, the connection between these two databases could be broken for some reason, or there's just very considerable latency. So for these benefits that feature stores provide, you have to consider the cost of data parity issues that two database systems provide. Splice Machine's entire organization, the entire structure of our system is designed to avoid that problem that every other feature store necessarily has by its design. How do we do this? We have a single database feature store that is entirely ACID compliant. What this looks like in practice is we build inside of the database, instead of an online and an offline database, we simply have two different tables. This one on the left is what we call the real-time feature serving table. These are the most up-to-date values of any given feature. As new data is added to this table, the old values are automatically sent to this training history table via database triggers. So here we have a time series representation of features in the past. And here we have the most up-to-date versions of those features for model serving. Now, because there's a single database, this whole system is ACID compliant. If there were to be an issue of some kind, if this process were to fail, it would revert back to a stable state. You never have to worry about data latency issues, data consistency issues, data parity issues. All of that is not possible in our system because of its single database design. We also think this single database design offers a few other additional benefits. First and foremost, it's easier to provision and operate. One database is easier to manage than two. Less infrastructure costs. Moreover, it's easier to back up and replicate. There's one system that is entirely consistent. You don't have to worry about two different databases and inconsistencies that may arise between them. No latency, as I mentioned. And finally, you get to take advantage of event-driven triggers. The data scientist is not responsible for taking data and sending it to the appropriate location. There's just much less work that has to be done on a day-to-day basis. The whole system is event-driven. As new data is added, the database triggers take care of the necessary data movement and move them to the appropriate places in an event-driven and automatic manner. I think I have a question in the chat here. So the next thing I want to mention is so that is our overview of Splice Machine in terms of the feature store. So you all were promised a demo, and now I'm just going to sort of talk about how the process of this demonstration is going to go. First, we are going to sign up for a Splice Machine free trial. I'm going to send you all a link in the chat, and you guys are going to sort of get started, spin up a cluster, spin up a database, and get started. I'm going to show you how to upload data, open Jupyter Notebooks, and query the database that we have. Next, we're going to create a feature store from scratch, show you start to finish how the feature store process works. You guys can do it yourself. Then we're going to train a machine learning model using some features from that feature store and deploy your model using the feature store, and then something we have called database deployment, which I'll explain in a minute. Finally, we're going to tie that whole story together, use the feature store and database deployment for model governance. Now, before we get started, I want to briefly talk about our user interface. Splice Machine is very excited to announce a brand new, very modern user interface in March. That's not what we're going to see today. We're going to see an old user interface that is used just for demo, just for trial purposes. So don't pay too much attention to that. We have a brand new user interface launched in March. that has all of the components that I'm showing you today, just in a slightly crisper format. So now it is time to go ahead and start the free trial. So what I'm going to do now is go ahead and post a link in the chat. Everybody can go ahead and navigate to this link and spin up a cluster. So what you'll have to do is either put in your name and your email, or log in through one of the affiliate OAuth websites here. If you do log in through your email, you're going to have to confirm your email address. We'll send you an email. You click confirm, and that'll get you started on the cluster. So I'm just going to give everybody a minute to go ahead, navigate to this link that I just put in the chat. Go ahead and sign up. And at this point, it'll be a good time for me to take some questions. We have a message here, super interested on the cost optimizer, how it works under the hood. Would you be talking a bit on that? Absolutely. We're actually going to bring in one of our SQL experts towards the end of the presentation, and he'll be able to shed some light onto sort of how exactly the cost-based optimizer works under the hood. So I'm going to give everybody just a few more minutes to sort of navigate to this link here. And I'm going to go ahead and head to the cluster itself, my cluster here. So in terms of following along, my hope is that you all will have the ability to follow along and sort of code with me as I walk through this process in a very hands-on manner. However, if you prefer to just watch me, that's great as well. If you would prefer to sort of, do it at your own speed and ask questions, that's great too. I'm going to go ahead and move on at a reasonably consistent, reasonably slow pace, and I hope that you guys will all answer questions when appropriate. So after you all have logged on, you will see a page that says start your 14-day free trial. If you go ahead and just click on that, you should then see a page that looks like this. I have 3 different databases here. You will have just one. It says cluster dash a bunch of numbers. So I'm going to give you all just another moment to sort of get to that point. If you have any questions about this process, feel free to put them in the chat. The question and answer session would be great. And so, like I said, at this point, I'm just going to get started. Feel free to follow along as best as you can and sort of code around in your own. So here we have the Splice Machine sort of landing page, the Splice Machine dashboard. What we're looking at here is an entirely Kubernetes orchestrated database and machine learning platform, complete with a SQL editor through Hue, Jupyter Notebooks, the ability to scale your database here. I can resize it depending on usage, and all kinds of other features. So what we're going to get started with is looking at the database itself. Here, this is what I'm going to show you now is just for the purposes of the demo, just the way this demo cluster is set up. The password that you logged in, the username and password is not going to be the same as the actual database password. You just go ahead and click on this retrieve DB password. For me, my username is just Splice and admin. Yours will be Splice and random numbers and letters. You can go ahead and just copy that. And what we're going to do first is we're going to open up Hue. We're going to take a look at the database that we have created. So I'm going to click on SQL Client here. And it'll launch for me Hue. Here I type in Splice, the password, and it'll launch for me a Hue SQL editor. So as you can see here, the trial cluster, the trial database that I've set up for you already has some data loaded, okay? So we've got the key pieces of data we're going to focus on for this demo are these retail data sets. So here are the schemas we have: retail, retail feature store, retail recency, frequency, and monetary. So we can go and click on one of these, and we can see the tables associated with this schema, in a typical, not at all unusual for a SQL editor. We can go ahead and query the database and see the results that are in the table. So what I'm just showing you here is that underlying the system, what the whole system is built on, is a single database. You can query it and interact with it however you normally would. So now I'm going to go ahead and close out Hue and just show you how you would connect to this database. You're more than welcome to use Hue built into our system, or you can connect to our database through a standard JDBC or ODBC connection to whatever platform you're using. If you have an application that wants to query our database, that's great. You want to use a different editor, that's great. JDBC, ODBC, all standard stuff. Now I'm going to go ahead and open the Jupyter notebooks, where we're going to spend the rest of the demonstration today. So when you open Jupyter notebooks, it'll look something like this. You'll see a couple of different folders. The one we're going to focus on today is obviously the TWiML folder. So I'm going to go ahead and click on that. Here in TWiML, you will see 5 different Jupyter notebooks. The first is create a feature store. So I'm going to go ahead and click on this and sort of show you how it works. And I hope that you guys have the opportunity to follow along as well. So here we have Splice Machine's Jupyter notebooks that are powered by our underlying Kubernetes architecture and connected with our database. The whole system, is designed for big data and it's designed for fast data. And because of that, it is built upon primarily Spark. So the first thing we're going to do is go ahead and start a Spark session. Here we just have a regular old Spark session. You can configure this, in some sort of custom configuration, for your organization's needs. And then we have this interesting thing called the PySplice context. This is simply a way to create a Spark data frame directly from the database without having to serialize data. This is particularly useful for big data applications, and it's one of the benefits of being directly tied to the database. We're then going to start up our feature store, and then additionally our custom fork of Mlflow. We have Mlflow as a part of our system, and we've added some important benefits, extra features to work with our system. So now, I think what you've all been waiting for, we're going to create a feature store from scratch. First step is to create a schema in the database. For this demonstration, we'll call it TWiMLcon_fs. That's already been done for you in this trial cluster. You go ahead and look at what schemas are available. You'll see TWiMLcon_fs right here at the bottom. The next thing we're going to do is what we call register a feature set. What is a feature set? A feature set is basically a data source, right? Wherever source of data is feeding into the feature store, it'll likely, you can imagine a table with multiple columns, or a Kafka stream with multiple pieces of data in it. Each of these will have its own feature set, and the feature store can have many feature sets. Here we're going to create one feature set. In this case, it's called customer lifetime. So what we're going to calculate here is some lifetime metrics for customers in kind of a standard sort of retail example. So the first function to do this is this create feature set function. This is just sort of putting into the system this idea. We're making a new feature set. It's called customer lifetime. We're going to specify the primary key of this feature set and also give it a description, which is just whatever the user specifies. Then we're going to go ahead and create features within the feature set. You can imagine these as columns within the table, right? We have customer lifetime active days. We have customer items per day, revenue per day, all kinds of different customer metrics. And what we're describing here is what feature set these features are going into, a description that the data scientist or data engineer can add, what type of data this feature is, and then any other tags the user decides to enter. These are, they don't necessarily do anything, the tags, right? They're not functional in the feature store. They're just for finding the data. In a later part of this demonstration, I'll show you a search feature. That's where these tags come in handy. And finally, you're going to go ahead and deploy this feature set. So we're going to go ahead and run that code, and we can watch it in action. This will take just a moment or two. At this time, while this runs, might be a good opportunity for questions, so feel free to put those in the chat. One thing to note here, as you can see, as I mentioned, our whole system is built upon Spark, and we just went ahead and added that Spark UI directly into the system, which very convenient. Don't have to switch to another tab to track the status of your Spark jobs. So here you can see we're registering the feature set. We're registering the features, and then just a moment, it'll say deploying the feature set. Great, that's it. So what have we actually done? You'll notice there's no data added here. There's no SQL added here. All we've done at this point is create two empty tables in the feature set, in the feature store, I should say. We have this customer lifetime table. That's what we specified here. And then the system automatically creates for you a second table, this customer lifetime history table. Additionally, it makes the set of database functions and triggers that link these two tables together. So we have empty tables inside of the database. The next step is to add data to these tables so that you have a functioning feature store. First, what we're going to do is just add some data to the feature table. I showed you before, there's some data preloaded into the system. We're going to go ahead and just add this directly into the feature store. Now there's data in the table. The next step would be to backfill the historical table. Here we have this big aggregation that is going to backfill, create those aggregations, and add it to the history table. Now, this is the simplest possible way that you can add data to the feature store, right? You've got some data. It exists in a database of some kind. It could be Splice Machine's database. It could also be an external database. Through our virtual table interface and external table functionality, we can query data directly from another database or even from a data lake. If you've got a Parquet file sitting in S3, we can create a database table out of that and pull it into the system. So this is the simplest possible way to add data to the feature store. And I'm showing it here basically for simplicity and time's sake. There are two additional ways that you could add data to the feature store, however. The first would be to add data directly to the real-time feature serving table. As I mentioned, as data is added, the old data will be moved to the historical table. So if you have your data, wherever it exists in a time series representation, you can just add that directly to this customer table. As new data is added, the older data will automatically move to the feature store, to the history table, and you can essentially sequentially add data to the feature store, and it will build the whole backfill table for you. This is probably the easiest and most practical way to do it, sort of in the real world. Takes a little bit longer, of course, because you have to sort of add data in sequentially. So I'm not doing it here, but that's how it might work sort of in the real world. The additional way is through a set of APIs. If you're not comfortable writing the SQL to create aggregations, we are happy to, we have some APIs in the works that'll sort of help you move those, help you build that backfill table for you. So at this time, what we've done is we've simply added data to both the real-time table as well as the historical table. At this time, I'm going to pause and see if there's any questions about what I've just discussed. Okay, I'm not seeing any questions. I guess that means I explained it perfectly. So I'm going to go ahead and keep on going. So as I mentioned, we have created two tables in the database. So let's go ahead and query those tables and see what they look like. Oh, I'm sorry. I was looking at the wrong part. I was looking at the question and answer and not the chat. There are a ton of questions that I've totally missed. I sincerely apologize about that. Give me just a moment and I'm going to go ahead and take a look at these and see what I can answer. So Thomas's question here. So basically what happens under the hood is now that we have two tables following the structure defined in code and a trigger responsible for syncing that tables. Could you comment on what else is happening? That's exactly what's happening, right? We have two tables inside of the database. They are linked together by database functions and triggers, as well as other metadata that is stored inside of the system. So in a certain sense, it's a simple architecture, right? We don't have a need to create this complex system of syncing two different databases. We don't have a need for a very complicated architecture. we have a hybrid database that is capable of both analytic and transactional databases. As a consequence, all that is necessary for a fully functioning feature store is this set of database functions and triggers, which we build for you. Does this build a star schema warehouse underneath? That is a great question. I'm going to defer that to one of our database engineers who's going to help us out with that later on. Would like to know more about pipelines and joins, basically the backend infrastructure and challenges around it. That's a great question. So because our system is all based around SQL, right? We have the transactional engine, we have the analytical engine. And our thought is that that is going to be capable of doing any sort of normal pipeline, you know, any pipeline and joins that are necessary can be handled inside of the database. It could also be handled outside of the database. If you have, you know, whatever current database you have set up, it's doing certain aggregations, you can just stream that into the database. You know, you could register a Kafka topic or a Spark streaming topic and take the feature set table as just the receiver, you know, the Kafka receiver of that data. The data streams in, and the feature store is operational. What is the logic of exposing a pair of tables rather than hiding the history table? That's a great question. So the feature set table is going to be used for model serving, right? When you have a model in production. The history table is also very important though. That's going to be used for model training. If you have you want to be able to use that historical data to train new models, and the historical table makes it very easy to do that. Next question is, how can this stay in sync with your transactional systems? So that's a good question. In one, perhaps the easiest scenario is this could be your transactional system, right? This is a fully ACID compliant transactional database. We have customers running, massive applications on the database. You could sort of unify and simplify your architecture in that way, right? You could have us be your transactional database. In terms of syncing to other systems, we can create virtual table interfaces as well as external tables. If you have another database, we can query that database directly and pull data in as necessary. So now I'm going to go ahead and keep on going. I apologize again. I was looking at the question and answer session and not the chat. I hope I answered everybody's questions thus far. Please keep on adding questions as appropriate. So as I mentioned here, we have two different databases, or two different tables in the database, I should say. We have the customer lifetime table and we have the customer lifetime history table. Here, we just went ahead and queried a single row, this particular customer ID, and we can see all of the features that are in the feature store. Then we have this historical table, which we can take a look at as well. These are the features at some point in the past. Here we have this as of until scheme, system of structuring the table. And we can see how the values have changed over time. So now I mentioned that the way this works is you would add data into the real-time table and the old value would move to the historical table. So let's go ahead and see that in action. What we're going to do is we're going to update this lifetime table, the most up-to-date value. We're going to change one of the values, give it the timestamp of that change, and let that run. So it's done. A feature has been moved from the real-time table to the historical table. That's all there is to it. It's just a simple SQL statement. So we can go ahead and see that change. In this historical table, we can see the data that was moved, right? This most recent row here, as of last year, whenever this fake data came from, until just now when I made the change. What do we update? We updated this customer lifetime active days from 9 to 10, or from 10 to 11, I should say. And the 10, the old value, was moved to this historical table. When we take a look at the current lifetime table, only the most recent value remains. Here you can see the customer lifetime value of 11, as well as the timestamp at which this change was made. So that's really as simple as the feature store is. It builds for you two empty tables inside of the database. you can populate that table, whether it be through SQL or whether it be through pipelines or whether it be through backfilling the historical table. And then using this table is as simple as SQL. You add data, data is moved, you're good to go. Now, the next thing to do is just to stop the Spark session so we're not using up unnecessary resources. And at this point, for those of you who are following along at home, it would be great if you guys could answer this survey for us. We're trying to get some feedback on our system, hoping to make sure that the key questions that people have are being answered. So you can go ahead and sort of maneuver through this this survey, and give us some feedback on how the system is working. So at this point, I'm going to pause again about this create feature store notebook. And if there's any other questions I could answer, now would be a great time. How would the update of table work? Okay, for instance, adding new fields, etc. That is a great question. So here we have this create feature set functionality, and we have individual features inside of that feature set. You can add additional features to the feature set. So it's pretty easy. And of course, you can make as necessary a new feature set. If this needed to be, if you had a new data source, you had customer lifetime, you could create, customer lifetime. You can create a totally new feature set. You can have as many as you would like. How can we define features that need to be updated in real time? For example, number of clicks in the last hour. So the feature store is all based around SQL, and as a consequence, you have the ability to write, any arbitrary SQL that you like. You can schedule a job to do an aggregation, every hour, as you mentioned, through a system like Airflow. We also have a number of APIs, as I mentioned before, that are in the works, and that's going to sort of essentially write that SQL for you, right? Build that system for you so that you're not responsible for doing it yourself. But the key benefit of this system here is that it's extremely, extremely flexible. You're not confined to the APIs that we write for you. It's a single database, ANSI SQL, that you can write anything you want. And so you don't have to rely upon, us building an API or a function for you. You have complete flexibility to schedule something like this however you would like. Additionally, source triggers can enable real-time calculations, right? Our database has full trigger functionality, and you can set triggers to fire at every set period of time to do these types of aggregations for you. That's something that wouldn't be possible with two databases, right? We have one database, one set of triggers that can all work together. Okay. And so I think at this point, I'm going to go ahead and move on from this create feature store notebook. If you guys have any other questions, feel free to put them in the chat. So next up, we're going to go ahead and pull up feature discovery. As always, we'll start by starting our Spark session. So here we have a question. Is there some kind of compaction mechanism to prevent the history table from exploding if we change features multiple times per second in response to real-time events? That's a great question. So let me say a couple of things about the historical table. The first is it's very easy to move the historical data to an external data store. So I'm not answering your question directly, I'm getting there, but a common way you might structure this is, say, the last 3 months of data are stored in the historical table, and then you move the older data, 3 months to the last 5 years, you move that into a Parquet file in S3, right? Very, very easy to do in our system with the external table functionality. Now, to answer your question directly, Splice Machine handles compaction as a background Spark process. So we do all kinds of compaction sort of automatically for you. And this applies to the update on current values. So sort of the issue that you've raised is something that we handle automatically for you. But the other side point I want to mention is if you're worried about that historical data from getting too large, and if you're don't necessarily have a business need to store historical data past a certain point, you can move that into some other data store very easily, such as S3, for cheaper storage, albeit it'll be slower to retrieve. So now I'm going to go back to this feature store for feature discovery. This is the first key use of a feature store. We built our feature store. We're going to do 4 things with it. The first is using the feature store for feature discovery. So what data do we have in here? We have a structure of data called RFM data, recency, frequency, monetary data. This is a common way of structuring data in retail examples, and it's exactly the kind of thing that feature stores really excel at. So the first thing we can do is see the feature sets that are available to us. There are going to be 2 feature sets available to us. The first is the feature set we built in the last notebook. That'll be the customer lifetime data. And the second will be a feature set that is already preloaded for us. It's a bigger feature set. There's I think over 100 features. We just have that sort of preloaded in here, for simplicity's sake. So we're going to give the system just a moment here to find the available feature sets for us. We see this first feature set, and we see all of the things we specified in the last step, right? We see the name of the feature set, the description, the primary keys that we specified, as well as all of the available features. This is the second feature set that I mentioned. This is customer RFM by category. These are these recency, frequency, monetary metrics that I mentioned before. We have a retailer example here. They sell multiple different things, clothing, food. We want to look at total revenue by customer, all these different metrics. Here we have 167 different features in this particular feature set. All this function does is just show us what's available to us. Here we have 2. You can imagine there being 100. Now, looking at data in this way, it's great, but it's hard to really get a sense of what's going on. So built into our feature store, and this is a common functionality of feature stores, is this display feature search function. So here we see all of the different features that are available to a given user. Because our database is governed like any regular database, you can have role-based permissionings, right? So these are the features that I have access to. You can imagine another user having access to different features. We have the features themselves, the feature set that they are a part of, descriptions, tags, everything like that. And we have this great search bar. So as I mentioned before, we have a retailer, clothing, deli, garden, all different things. We can type in garden, for example, and we can see all of the different features associated with the garden. We go ahead and click on one of these, and it'll build for us the distribution of the feature that we clicked on. So we're not getting a ton of revenue out of the garden section. Let's try another one. We can take a look at the deli, take a look at this feature here, and see the feature distribution as well. So this functionality, I think, gives data scientists a few things. The first is it lets them know what features are available to them. Other data scientists and other parts of the organizations, other data engineers are building features. If you have a model you want to train, you can very easily in one search bar see every feature from every feature set that is available to you. See where it is, what it is, anything that you want. And the second is it stops duplicate engineering efforts, right? I think a very common thing that happens in many data science organizations is a data scientist will spend all this time making a feature, not realizing that some other part of the organization has already made that feature. There's enormous duplication of effort that a search bar like this and a feature store in general can reduce. Now, just a quick note about this search bar. Because the whole system is SQL, you can easily write your own search functionality, right? All we have is SQL tables. If you need some kind of custom search capacity, very, very easy to make that. You can just write some easy SQL. Once again, you're not confined to our APIs, right? We have built these APIs for you, but what they're built around is the database. The database is the key component. And so any custom functionality that you need is very, very easy to create. Now, we are in a notebook now, but it doesn't have to be in a notebook, right? Through the JDBC connection or the ODBC connection I showed you at the very beginning, you can connect to our database and build this search bar and then some kind of application. If you have some sort of data science workbench in your company, very easy to add this in. Once again, you're not confined to what we make, very flexible. So at this time, I think I'll pause and ask if there's any questions about this feature search functionality. Is there a place to document what each feature means in case a person who doesn't create the feature store didn't have intuitive naming? That's a great question. So I'm going to go ahead and move back to where I created the feature store, this first notebook here. And you'll see in the code, whenever you create a feature, you are required to add in certain pieces of information. So one thing is the description. You can say, what is this feature, right? What is it that we're talking about, right? And then there's also different tags. We have a customer feature of lifetime, the metric, is it a count, is it a sum, is it an average, is it a duration, what's the unit of measure, what's the granularity, all of these different things are part of the feature store. And in the search functionality, instead of searching for function, searching for deli, you can search based on the description. You can search based on the tags. All of these, different, however you want to search, you can add in as part of the metadata associated with each feature is extra information, as you mentioned. Can you add your own fields to the feature store attributes? Absolutely. This tags field is completely flexible. You can put in here whatever you want. You could imagine your organization has its own custom, mechanism for governing these tags. Feel free to use them. Feel free to use them as you want. What would query based on tags look like? It would look exactly the same. If I want to type in day instead of what I had before, you'll see here in the entity here, time granularity is day. So day is returned for me all of the different day features that's based querying on this tag. I think we can also do week here. If my memory serves me right, that's what the other features are based on. And we can see that the only place you'll see a week in here is in this tags. Time granularity in this case is week. You can query based on the tags, query based on the description, query based on the names. Once again, just at risk of repeating myself too much, the system is all SQL. So you can very easily write your own query for any, for any type of search that you're interested in. Okay, great. So I went ahead and stopped my Spark session. And then once again, if you guys would take the time to fill in the feedback form, we would greatly appreciate it. So I'll give you just a moment to do that and answer any questions that may remain. Is there a visualization tool to see all of the features and their relationships? So we do not currently have a tool that looks like that, but that's a great feature and something that I think will be coming soon in Splice Machine. Because it's SQL though, you don't have to wait for us to make that for you, right? It'd be pretty easy to write the SQL that sees where the feature sets come from. Any particular thing you want can be easily extracted. Are there options to add data types? Absolutely. Whatever data type you want, be our guest. Let's say that we have two feature sets. One is 100 records and the other is 150 records. If I want to use both of them, where would the logic to combine them happen? I mean, I would have 100 records for both feature sets or 150 records where 50 are empty for the first feature. I hope this makes sense. Let me read this one more time and make sure I understand the question here. I understand. Great question. I'm actually about to show you. So if you'll hold on just for a moment, Thomas, I will show you sort of how that works. Okay. So are those search queries going to the database or pandas in memory? Great question. It is going to the database. which is scale out, right? As big as it needs to be. Yeah, I should mention that almost no part of this system is in memory in pandas, right? Everything is governed and executed by the database in a scale out fashion. I mentioned very briefly the native Spark data source. What that means is your Spark data frames don't have to be loaded in Jupyter. They are stored in the database. You don't have to waste your Jupyter memory on a monster Spark data frame. So here we have the 4 uses of the feature store. The first was this feature discovery. Now I'm going to go ahead into the second, which is model training, the second key usage of a feature store. So feature stores can be used for any type of model training, right? Whatever your sort of training set looks like, feature stores are a great way to create that training set. But feature stores are particularly good at making what's called a point-in-time consistent training set. This is something that I don't think all data scientists realize how much work they put in to do this. They don't realize that making a point-in-time consistent training set is something they're already doing. It's something that is very challenging. And it's something that's much, much easier with a feature store. So what exactly is this point-in-time consistency problem? So in the real world, features are updated at different times, right? And how do you join across asynchronous timestamps? Imagine this sort of very simple example here. We've got a couple of different features. You can imagine each of these being a feature set, or a data source, right? Maybe they have 100 columns associated with them. We're just focusing on one of each of these data sources for the purposes of this little picture. We've got, in this case, like a website, right? They're navigating through the website, picking out things to purchase in our retailer example, how many times they search, how many items are in their cart, and how many products they've actually viewed. And we're making predictions at various different points. You can imagine, for example, that this is like a customer recommendation engine, right? After they've looked at certain products, which products do we recommend to them next? At any given point, we're going to have different features that are available. So if we were trying to make a training set at this point, right, we're trying to predict, what should the model, what prediction should the model make at this time? It would be challenging to get all of the most up-to-date features because you'd have to join them you'd have to join these asynchronous timestamps, right? You'd have to have some kind of moving window to join everything together. So in this case, the most recent features would be from this first one 2, and this one 0, and this one 6. Now, I was talking to a data scientist at TWiML just the other day, and they were saying the way that they had solved this problem in the past is they would sort of pick one of these timestamps, right? They would say, okay, we're going to join at this particular time, and whatever features are available there is what we get. So maybe we get the second feature, feature 0 here, and feature 4 here. This is a problem. You've got stale data, right? There are 2 new data sources that your model should be trained on that you don't have access to, because you don't have an easy way to join everything together and build a point-in-time consistent data set. What's worse is if the reverse happens. If you make some kind of error and you add in the second prediction, feature number 7 or feature number 8, then you've got data leakage. Your model is being trained on data it otherwise shouldn't have access to, right? And this can be a real problem for organizations. Now, as I mentioned, building a point-in-time consistent training set is something that I think data scientists do all the time, even if they don't necessarily realize it. And it's a lot of work, but it's doable, right? They're all very, very smart, very talented people at this conference. You can do it once or twice, no problem. What about for your 5th or for your 50th model, right? To join together all these asynchronous timestamps in a unique, bespoke way for each model quickly becomes a nightmare of ETL pipelines. So this is one of the key things that a feature store does, right? It'll build for you with like one function, which I'll show you in a minute, a point-in-time consistent training set that looks something like this, right? So in this sort of fake demo example, what we have here is we're trying to predict the total customer value based on that customer's first 4 weeks with us as a retailer. Purpose of this being, if we see a particularly high value customer, such as this particular customer ID here, maybe we give them an extra touch point. Maybe a sales representative reaches out to them personally. Now, in their first 4 weeks, like what is the first 4 weeks is going to be different depending on the customer, different timestamps. This guy's first 4 weeks is in January. This one is in May, right? So it'll be different. So to create that this and it won't even start on a Sunday, for example. Their first day could be a Tuesday for one person and a Sunday for another. And then so you need all of the features that are available at this time and only the most up-to-date features at this time. Feature Store will build this table for you. How does it do it? It goes back to Lee's question earlier. Why do we expose this historical table? This historical table allows you to build a point-in-time consistent training set like I showed you above. What do we have? We have a time series representation as features looked in the past with both the primary key and then an as of and an until timestamp. So let's go ahead and do this. Let's build a point-in-time consistent training set, and I'll sort of show you how that works. In this particular case, we have a labeled, a structured machine learning problem, right? We have a label that we're trying to get data for, and so that's what I'm going to focus on. If you have unsupervised, if you have an unsupervised problem, you can totally use the feature store for that too. Just for the simplicity of this demo, I'm going to focus on a supervised model because it's kind of the easiest to wrap your head around. So the first step in building a point-in-time consistent training set is getting your training label. You can write any arbitrary SQL to get your training label. In this case, we have a real simple aggregation that is going to create for us this customer lifetime value. You can imagine this is as simple as like select column name from table, right? Any arbitrary SQL necessary to get your training label. Then we're going to create what we call a training view. So how does this work? Just 3 steps. The first is we specify this arbitrary SQL to create your label. In this case, simple aggregation could be anything. You then specify the primary keys of this training label that you've created, and you specify the join keys. So in this case, we're talking about customer ID. We're going to get all of the features for each customer ID, right? You could imagine other join keys. That's what we have in this example. We then have this create training view function. We specify the SQL, we specify the primary keys, we specify the join keys, and we give it a name. In this case, TWiML customer lifetime value. What this does for you is it joins together all of the different feature sets that are available. So you have 2 different feature sets with different numbers of features. It joins together in a point-in-time consistent way the training set that you need. So we're going to give this just a moment here. And what this is doing here is it's registering this thing in the feature store called TWiML customer lifetime value. So we now have a new thing in the database, right? So how do we take a look at it? Very simple. We just get training set from view. Here's this view we specified above. We're going to go ahead and get a training set from it. And what this, my apologies. What this creates for you is a Spark data frame. In this case, I'm just setting it to pandas just because it's easier to view. Looking at Spark data frames can be a little hard sometimes. And this is building for you that training set. So let's give this a moment and we'll take a look at what this looks like. Yeah, the 2 pandas part is the one that takes the longest. I guess at this point, I'll pause again and see if there's any questions about sort of what I've explained thus far. About the idea of building a point-in-time consistent training set. And then here we are as the Spark data frame that we created above, just shown in pandas, right? So we have the customer IDs we care about, what week they are, right? Is this their first week, second week, third week with us as a customer? What is that timestamp? When is this? This could easily be a feature in the model in and of itself. And then the features themselves, right? What were the different metrics at the point in times that we care about? You can see as they change. And then we have the training label. So what we're building for you is this point in time consistent training set. This is obviously a really small demo cluster. It takes longer than it normally would, but finding every single feature that is available for a given training label is as simple as writing the SQL to get that training label, specifying what the primary keys are, and then calling these two functions. That's it. It finds every feature, could be across 100 feature sets, joins them together, and only gives you the applicable ones. Makes it much, much easier to create training sets. Now, how does this work, right? So what has actually happened here in this magic function, create training set from view? Like, what has occurred? What it has done is it written SQL for you. The whole table, the whole database is governed by SQL, ACID compliant, ANSI SQL. It writes SQL for you. So what I'm showing here is instead of returning the Spark data frame, I'm returning the SQL that was created. So give this just a moment and we can see what that SQL is, right? We've got this huge, nasty SQL statement, right? We've got all these different coalesce functions. We've got inner joins, we've got outer joins, we've got subqueries. This is what would be necessary to build a training set like what I showed you above. But because of the structure of the feature store, it builds this entire thing for you. Additionally, this function is set up so we build an optimized query for you, right? We know our database well. We've designed our functions to use it optimally. Now, a key point I want to mention here about this training set is that this operates like a SQL view, right? If you can imagine, every time the data changes and you rerun this function here, you will get the new, most up-to-date training view, right? There's no need to version the data. There's no need to persist data frames at every particular point in time you care about. Every time you rerun this function, you will get the most up-to-date training data. It operates like a SQL view, which is only possible because of our single database design, right? And so to really touch on Thomas's question from before, we've got different numbers of rows. That's what's handled for you by these coalesce statements, by these inner joins, by these subqueries, right? We're building for you the point in time consistent training set. Now, you're more than welcome to write this SQL on your own if there's a custom training. I'm not really sure the use case in which you would need to, but you're more than happy to, more than welcome to, I should say. The next thing I want to mention, so I guess I'll pause here about the creating of a training view. We've created a training view. All you have to specify really is the training label, and it'll find for you all of the different columns that you care about. So are there any questions about this point here? Great. So the next thing that I want to mention, this was a question that was asked in our demonstration last week. Let me pause right here. You specify a single timestamp column. Is it possible to specify multiple? That's a great question. I'm going to, I don't think that is possible. I think that you would have to specify the one point in time. There's sort of one timestamp is sort of how this whole system is built. Keep in mind, in that training, in the historical, in the real-time feature serving table, right? We have we have the timestamp we care about, but in the historical table, we have a time range, like the from and until, right? So what is that? What are the time period in which that feature exists? The timestamp column is defining the temporal join, right? That's how we create the point in time consistent data. That what is this timestamp here? This is like when this feature existed, if you will. So that's sort of what's going on here. I notice that there are two parameters called start time and end time. Could I assume that they're used to version the query based on the interval I'd like to retrieve? That's exactly right. Yeah, that's a great question, Thomas. That's exactly how that works. Great. So we have created our training view. And we have a ton of features here, right? Tons and tons and tons. A very common thing to do in data science is some kind of feature selection, right? Maybe we only want the 10 most relevant features for our modeling process. Our feature store and really feature stores in general make that very, very easy to do. So how do you create, how do you do sort of an automatic feature engineering process? All you have to do is specify this training view. So here we're getting all the features from the training view we specified above. We're gonna go ahead and drop some of these. So just of the 100 or so, of the 150 or so, we're gonna just focus on the 100 or so that make sense to put into our model. And now we're going to create a Spark data frame with all of the features that we care about, right? Get training set from view, and we're going to specify the features being only the features that sort of make sense to put into our model. Then we can do really any kind of automatic feature selection that you would like. As part of our feature store, we have this run feature elimination algorithm. You can imagine using any other algorithm that you want. You're in no way required to use this one. But we include it. It's sort of a standard linear regression model of finding the features that have the biggest impact on your label. And once this process is done, it'll this is feature selection takes a long time. It'll give you this string top features, right? All of the 10 most relevant features as they relate to our training label. So in this case, we can see the 10 labels that we have specified here. So if we want to make a brand new training data set with just the features that we care about, it's as simple as get training set from view we've seen before, and we just set the features to this top features that we did above. So what this allows you to do, what the feature selection plus the feature store gives you, is incredible automation of model training, right? Imagine a feature engineer or a data scientist, somebody in that process adds a new feature to the feature set. You can imagine this run feature elimination process running monthly, weekly, hourly, whenever. And you just make a new training set with just the most performant features out of all of the features that are available. This whole system can be automated. At no point are you required to sort of specify anything, right? Makes it very easy to build training sets for you, sort of putting that whole package together. So are there any questions? Once again, I wouldn't pay too much attention to this particular feature elimination algorithm. It's just one we've included. You can use any that you would like. So now that we have our most performant features, let's go ahead and train a model. So as I mentioned at the beginning, Splice Machine's system is really structured around Mlflow. This is not just regular Mlflow. We have added to Mlflow a number of really key pieces of functionality. The first and most obvious of which is, Mlflow has to store this data somewhere. If you use Mlflow on your own, you're responsible for setting up some kind of repository to keep this data in. All the relevant Mlflow metadata is just stored in the database, right? We just make a new schema, new tables. It's all entirely taken care of for you. You just literally import our own sort of fork of Mlflow. Don't have to do anything. So I'm not going to spend a ton of time on Mlflow here, but just know, a part of Mlflow is this user interface. We can see the different models that we've trained and various things about them. So what we're going to do now is train a model. As I think is kind of stock in Filmicon, don't pay any attention to this particular model, right? It's a linear regression. The point here is not to show like what this model is or talk about the best types of models to train. That's what the data scientists are for. But you can train a model however you would like, log it in Mlflow, right? So here we're gonna specify the experiment that we have. The project is this, team is Jack, that's me. I'm the team member working on this particular project. We have a linear regression. And it's logging the process in Mlflow. Through Spark, we can sort of see the training in action. So we'll give this just a moment here. You can see the coefficients. Should give us the R² value in just a moment. Excellent, and I think we are done. So now we've trained a model. The particulars aren't important. In this case, it's just a linear regression. And we can go back into Mlflow and see sort of what's been logged and see some of the key additions that Splice Machine has added to its Mlflow process. So let's go ahead and look at the time. Today's date is the 28th. So here's this model that I just trained here. I'm gonna go ahead and click on that. And the first, key thing that should jump out at you is we can see all of the parameters that were used to train this model. That's one of the things we logged up above, right? So we have all of the columns that were all the parameters used to train the model. You can imagine if you're using the feature store in conjunction with automatic feature elimination, this is particularly handy. And any given day, the top 10 most important features might be different. We can see whatever metrics we choose to define. In this case, we just defined R squared. You could imagine calculating a million other things, F1 score, accuracy, mean root squared error, whatever, they all go here. We then have this run ID, which is literally what the model is, right? This is just an ID that Mlflow uses. And this is a really interesting part here, this database transaction ID, right? So what this means is this is a log. This is a timestamp of what the database looked like when the model was trained. So if in a year from now you want to say what did the data, what was going on, what were the raw data, what were the features, what happened here when this model was trained, you can sort of go back in time, rebuild the database to look like how it did in the past using this database transaction ID that's logged here. We then log whatever else we choose. I ran it before I changed my name, but a million, infinite things you can log here. We then have what's called artifacts. So the first is the literal model itself. We then have the Jupyter Notebook that was run. Key point here, this is not just a copy of the Jupyter Notebook. That's great, but the unfortunate thing with Jupyter Notebooks is they could be run out of order. They could be executed out of order, which makes it difficult to really have that full governance story, to really look back in time and see how a model was built. What we have here is not just the Jupyter Notebook. We have the Jupyter Notebook in the order in which the cells were executed, right? It just so happens I ran this notebook linearly, but you can imagine I ran this cell before this cell, that would be reflected here, stored, memorialized, ready to go when the auditors come knocking, right? And then we have the Jupyter Notebook itself. So all of this is saved persistently in the database that can be accessed in the future and also shared across teams. So we've created a model, we've used data from the feature store to do so, and we've logged that process in Mlflow. What I'm just gonna do here is I'm just gonna go ahead and store these top 10 features because I'm gonna use them in the next notebook. Are there any questions that I can answer about this model training process using the feature store that I've just described? The other key thing I just want to mention here is, with the features, we talk about the start and end time of the features, right? So we can see, really see what the data looked like when we trained the model. Okay. So at that time, if there's no questions about this model training process using the feature store, what would be the process to retrieve based on transaction ID? That's a great question. I'm going to show you that later on in the demonstration. Great. So I'm gonna go ahead and stop my Spark session. Once again, if you guys would take the time to just, give us some feedback on this process, anything that's unclear, put it here, put it in the chat. And I'm going to move on to the third key use case of a feature store, which is model deployment. You'll hear this called model serving, model inference, it's all the same. I'm gonna show you how a feature store can be used for this process. Now, the title of our talk is Feature Store and Database Deployment. So I'm going to transition slightly from the feature store and move into database deployment. So let me talk about model deployment just for a moment. The traditional way to do it is with a REST endpoint. You set that up, maybe it's in a Flask app, maybe it's in Azure, maybe it's in SageMaker. It exists somewhere in the ether. You hit it with a REST, with a REST endpoint. Come get the results. They get the results back. There are, I think, complexities and limitations with this system that are not always obvious. The first is performance, right? You now have a whole nother system you have to scale. You have to scale your, whatever engine is powering your model deployment separately from wherever the data is. Just another cost, another complexity. And the second is permissioning, right? Your company already has permissions for its data and for its models. You have to create a whole separate set of permissions for your deployed models, right? You need another system to decide, another authentication mechanism for who can access this REST endpoint. The third is with model governance. The basic way to set this up is, data goes in, a prediction is generated, but maybe an application uses that prediction. But what becomes of the data, right? What data was used to create the prediction? What prediction was actually generated? If you want to go back in time, and if you want to look back and say, over the last month, what predictions has my model made? It's definitely possible to do that doing a REST endpoint. It's just a whole nother system you have to set up, right? You have to figure out a way to take the data from the REST endpoint, send it to a database, clean it, a lot of steps, right? And so a simpler way of doing this is doing it through the database. And that's something that is, I think, really catching on, really becoming more popular. I think here at Splice Machine, we really believe that for many, if not most applications, deploying a machine learning model inside of the database is the best way to do it. And I think we're really heartened where we see a lot of validation that other people are starting to agree. Redshift ML was announced in December. Vertica has been doing database model deployment of some kind for a while. But these systems, these systems, these other database deployment systems that exist are not complete end-to-end machine learning solutions, right? Take Redshift ML, for example, which is a great product in many ways. You have to train the model inside of the database. Additionally, it can't be used for real-time feature serving. You can't power an application based on Redshift. It's not a transactional engine. So we love database deployment. We think it's the easiest way and the best way to deploy machine learning models. And we took our transactional database with our hybrid database with transactional and analytic capabilities and applied that to this idea of database deployment, which makes it by a margin much more powerful than any other system of deploying models in the database. So let me talk about sort of in specifics what exactly is happening here. Database deployment means you create a table in the database like any other, but it has a series of functions and triggers associated with that table, such that whenever new data is inserted into the table, a prediction is automatically generated and stored in that same database table, as well as metadata. Metadata being who asked for the prediction, when, the run ID is what model was used to create that prediction. And so in our system, in the database deployment as we define it, you don't train the model inside of the database. You can train any scikit-learn, Keras, H2O, or Spark ML model you want, however you want. You want to train that model in the Jupyter notebook we saw before, using our fork of Mlflow, be our guest. You want to train that model on your own. You have a model you trained 5 years ago. That's that's great. We basically create for you a user-defined function, turn that model you've created into a function, make a trigger for you such that whenever data is inserted, the prediction is generated. So we think there are 3 key benefits really of deploying the system in this way. First, it's fast. There's no network latency. Your data and your model exist in the same place. Data doesn't have to travel from wherever it exists to the endpoint and back. Maybe it has to move to a storage location. None of that is necessary. No data movement, all in the same place, governed by a transactional, ACID-compliant database. Second, it's easy to deploy and govern. You want to look back in time and see how this model performed. You have a tabular, clean version of every prediction the model has made automatically. I was speaking with somebody at TWiMLcon just a few days ago, and they were saying something like this is something they would really love to do, right? They would love to see what predictions the model has made in the past. They just haven't had sort of the time to put that together. With database deployment, there's no, it's just automatic. It's just built into the system. It's also very easy to deploy, which I'm going to show you in just a minute. And finally, it integrates directly with the feature store. So I'll go ahead and show you that now. So here's Mlflow, which I showed you before. What we're going to do is just get those most important features that I created in the notebook before, and then these two cells here is all it takes to deploy a feature store, or I'm sorry, to deploy a model into a database table. Here we're just creating a schema and dropping a table if they already exist. And this is brand new, so not actually necessary in this case, but just good practice nonetheless. 2 steps for deploying a table into the database. First is to get the training data. This is just so the table knows like what columns to make, right? What are the input columns going to be? We're just going to sort of specify what these columns are. And the second is just this one function, Mlflow.Deploydb. Now, this is a function that we've added to Mlflow. This is not found in sort of the regular open source version of Mlflow. And all you have to do is specify the deployed model, or I'm sorry, specify the table that you want to, the schema in the table, and then this Mlflow run ID. This is what I showed you before. So if we can go ahead and open up Mlflow, we can take a look at the prediction that the model that we trained just a moment ago. And we will see here that it has this run ID. We're just going to go ahead and copy that and add it right here. And that will be the model that we deploy. This could be any model you train however you want. If you have an old model that you've trained, you can just easily register that in Mlflow. And here's the model that we are deploying into the database. And then all this here is just, we're just going to watch sort of the process happen. Getting this data frame will take a moment, and then the actual deployment itself takes typically about 15 seconds. So we can go ahead and see that in action. And once the logs start going, you'll know that the actual deployment process has begun. So as you can see here, here's what's actually happening under the covers, right? We're deploying a model to the database. We're creating this empty table called deployed models TWiMLcon regression, right? These are the columns. These are the features that the model requires. Then as you can see here, we're creating a trigger. This particular regression model with the run ID that we specified above. This is a trigger that calls the user-defined function that is the model. Whenever a new row is executed or is added to the table, the trigger fires and the model prediction is automatically generated and stored in this same database table. As you can see, started at 04, finished at 13, took like, almost always under 15 seconds for this process to work. So now we have an empty table inside of the database, right? If you want to make a machine learning prediction, you just insert data into that table, the prediction is generated. This is where the real-time feature serving side of the database comes into play, right? All of the most up-to-date features you would typically add into this table and generate your machine learning predictions. So how does this work? In Splice Machine, we define features from the feature store used for model serving as a feature vector. Here, what I'm making is just a Spark data frame. We're specifying the feature list. These are the 10 features that I specified above. These are the 10 most performant features, from the last step. And then whatever the join key we care about. Here we have a particular customer ID. And here's the literal data, the literal features. I think we've got a bunch of zeros here in a Spark data frame form. Now, in practice, that's great if you've got a monster data set. For any kind of batch aggregation, getting a Spark data frame is probably the best way to do it. But for real-time application, that won't be the fastest way, right? Making a Spark data frame takes time. So what we allow you to do is instead of generating a Spark data frame, you generate the SQL, right? It gives you the SQL used to create the feature vector. And then if you want to get all the most up-to-date features, right, we can copy this SQL that was created for us. I'll just get rid of this old one here. Oops, give me just a moment here. Add in this new SQL and give it a run, and it'll get that data for us very, very quickly. Now, what we see here, this wall time of 1.2 seconds, this is not the database time, right? We're doing this in a Jupyter notebook. We're generating the features, into the notebook. What takes a long time here is the Jupyter notebook. Also, we're on a really small cluster, so this is not sort of the use case for sort of performance benchmarks, performance testing. The fastest way to do this would be, through a SQL shell. That's how you would do it if you had a real-time application running. And we're happy to, in more detail, go into the details. For most applications, our SLA is sub 20 milliseconds, right? This is an extremely fast process due to the single engine, due to the transactional nature of the database. So we've got our features. We need to insert them into the database. Let's see how that works. So we've got this table here, deployed models, Tomocon regression. There aren't obviously any rows in here, but we'll just truncate it for good practice. And excuse me, all that is necessary here is to create a machine learning prediction is an insert select SQL statement, right? Insert into this table, select data out of the feature store. This is the query that the feature store wrote for us before, right? Here we're doing 2 rows. We'll go ahead and run this. And this happens really, really fast. And the key point here is that in real life, it would be even faster, because if you had an application that was doing lots and lots of inserts into this table, you would create a prepared statement in SQL, right? So this process is optimized. In this case, obviously, this 800 milliseconds is just the Jupyter Notebook wall time. The real execution is much faster. And we can go ahead and see the predictions that were made, right? So here are all of the features that were generated. Let me move this down here. Here are the features that were generated. Here are the predictions. This prediction here is just one column. It could be multiple columns, right? You can imagine it being a classification. Here we have a regression problem. You can imagine a classification problem with multiple different columns and the weights associated with each classification. What this outputs is whatever the output of the model is, right? It's not the output, it could be anything. And then we have the metadata associated with it. Who made the user? Right now my username is just Splice, when, and the run ID. Adriana asks, will you talk about continuous monitoring? What out-of-the-box configurations has Splice Machine made? That's an excellent question. My next notebook is devoted entirely to that question. So if you'll hold on just a moment, Adriana, I will get to that. And the next is, can we use non-standard ML libraries, custom ML models for the predictions? Excellent question. So for database model deployment, as I've shown you here, all we support currently is scikit-learn, Keras, H2O, and Spark ML. And we are planning on adding more as time progresses. However, because our entire system is Kubernetes orchestrated, you can deploy a model to the Kubernetes pod directly, anything you want, and the whole system is linked. You still get many of the benefits that I've shown you before, right? There's no data latency, everything is contained together. So you can deploy anything you want, any custom model. It's just a little more complicated than what I've shown you here. I'm not gonna get into that in any more detail here. I would be happy to set up sort of a one-on-one and show you that process. But for the 4 libraries that I've shown you now, and also more to come, it's this easy. For any custom model, it's only slightly more complicated. Great. So what we've done here is inserted 2 rows into the database, right? How would this work in real life, right? You've got an application that's connected to our database. You've got, some parameterized code, some code that creates some parameterized SQL, generating insert select statements, making the prediction, generating the prediction back from the database, using it for whatever, the whole process being logged and stored throughout the whole system. So this is for two rows of data, right? This is a real-time transactional example. What if you wanted to do a big batch aggregation? It's exactly as easy, right? Instead of inserting one row into the database, you would insert however many you want. In this case, we're inserting like 130,000. We're on a real small cluster here. Just for the purpose of this demonstration, we're going to send this, we're going to force this to go through Spark. But you can imagine that because of our hybrid database, this can execute, in the real world in your actual business setting, this will execute through Spark, right? So it's able to do a big batch aggregation in a very efficient process. As I mentioned here, small cluster, this will take about a minute, but this process scales with the size of the database. You have a bigger database. The ability to do big batch predictions will be much faster. So I'll give this just a little more time to keep going here. This case, like I said, took about a minute. And so we can go ahead and select from that table and see the predictions that were made. Here we've got 10 different, I just did a limit 10 here, 10 different predictions, all of the predictions that the model made, who made it and when. That's how the system works. And so just to pull the whole story together, right? Deploying a model is as easy as a deploy DB function that we've written for you. You don't have to write any new permissioning schemes, right? It's all orchestrated by the same user-based, role-based permissioning that you probably already have in your database that people are familiar with. You don't have to link together multiple different data sources and engines. You don't have to figure out a way to connect your REST endpoint back to your database. It's all self-contained in an extremely performant manner. So I'm going to go ahead and stop the Spark session here. I'll pause again if there's any questions about database deployment, right? And so these two things, just to be clear, can be used independently. You want to use database deployment without our feature store? Great. You want to use the feature store without database deployment and deploy them to Azure? Be our guest. But together, they're particularly powerful. Why? Because we're generating these insert select SQL statements for you. All of the data is coming, from the feature store and using that real-time feature serving table we create for you. The whole system just works together beautifully, but totally can be used externally. If you're not interested in deploying models in this way, just want to use our feature store, that's great. Do you have any available benchmarks for real-time latency? We do. So we have HTAP benchmarks on our website. I can send you those after this talk. And then we are in the process of working with the other people in the feature store space to make a more consistent set of feature store benchmarks, right? So how would the feature store work in conjunction with this process? So we do have available benchmarks, and I'm going to follow up with you to give you those precise details. They obviously depend, on a number of factors. I should mention though, it's very, very fast. In my own experience, 10 milliseconds is a slow execution. So at this point, feel free to, please take the time to fill out the survey. And I'm going to go ahead and move on to the next part here if there aren't any additional questions about database model deployment. So the final step here, the fourth use of the feature store, is this model governance, this feature governance story. And this is getting directly to Adriana's question that she just asked, right? How is this whole process tied together? So in this case, I've actually already run these functions. They take, I think this one's about a minute, this one's about 5 minutes. So feel free to run those on your own. I've just run them already for the purposes of this demonstration. But what we have here is the first sort of built-in function into our system, which is this display model drift, right? All you give it as an input is the model table that you're interested in, and then however many time windows you want to see. So what are we seeing here? The distribution that the distribution of predictions the model has made over time. We can track as predictions have drifted. How are we able to do this so easily? Every prediction the model has ever made is stored in that database table, right? It's all right there, ready to go. So we generate this, this histogram for you. Now, the point here is that we have this function here. This is not a real-time function, right? This is sort of after the fact. You can imagine very easily turning this into a real-time tracking system, right? Maybe you have a Grafana dashboard, excuse me, or some kind of Tableau dashboard, anything you want. We have just a standard JDBC driver. You select, you create whatever custom histogram or graph that you want. It's very easy to make that real-time table, have this update every second or every 10 seconds or every hour, because it's all just based around SQL. You're not confined to our APIs, although we do have many available. So this is just for the predictions themselves, right? This is really a function, not so much of the feature store, but of the database model deployment. When you use database model deployment and the feature store together, however, you can sort of take this governance story a step further. We can look at feature drift over time, right? So in this case, it's the same thing. We specify the deployed models, and we specify the schema and the table of the deployed model that we care about. And this gets back to Lee's question earlier. Where does the database transaction ID come in? It comes in here, right? We can see what was the distribution of features when the model was trained, right? So that is specified by blue here, right? What did the data look like yesterday, an hour ago, a year ago? Whatever data went into the model, we can reconstruct that and build that distribution. That is because of the feature store. The feature store gives us that capability, and we have a function that lets you easily visualize that. The orange is the features, is the distribution of features that the deployed model itself has seen, right? The features could have drifted over time, right? In this particular case here, we see that the distribution of data that the model was trained on and that the deployed model has actually seen are very different. And that could be a big problem for your model and something that your data science team needs to take a look at. Or they could really have not trained all that much at all, right? The distribution is more or less the same. So to get this orange side, right, to get the distribution of features that the model has seen, we just query the deployed model table directly. And then to make this blue side, this training side, we can query the history table, right? And we can use that transaction ID to see what did the data look like at the point in time in the past when the model was trained. So as I mentioned before, this type of graph can be very easily converted into some sort of real-time application, real-time dashboard, I should say. In this case, we have these sort of static functions built into the system, which of course in themselves very valuable. You take a look at this every month, but it's very easy to make it your own, right? It's just SQL. Your company is almost certainly going to have some kind of custom, governance metrics that you care about. In order to create a graph like this, you just query the database, right? You don't have to, learn anything new really in order to do something like this. So let's sort of complete the circle, take this governance story all the way around and see feature store, model deployment all together. Why is this so powerful from a governance perspective? Let's say that somebody comes to you, a regulator, another member of your organization, your boss. Why did your model make this prediction, right? Maybe there's a concern that there's fraud. Maybe, there's a concern that the model was trained poorly. You need to be able to defend yourself when, if you did things correctly, and you need to be able to very easily debug, understand the process if something went incorrectly. So in this case, we have a particular customer ID that we care about. Maybe that's the one the regulator is interested in. And then the time, right? In this particular week, what predictions were made. Give this just a moment. And we can see every prediction that was made at these various points in the past, right? What features went into the model, what predictions were generated. In this case, they're all the same, but you can imagine them being different. And who asked for the prediction, as well as what model was used to make this prediction, right? So if I go back into Mlflow, I can search for this run ID, this DC, OB, whatever, right? Find it in Mlflow. It'd be this one here, and see what features went into the model, right? What is the accuracy of this model? What did the database look like? Who trained it? What Jupyter notebook was used to train this model, right? You have a full end-to-end story about why any prediction was ever made. Who trained the model? What features went into that model training? What features went into the model prediction itself, right? All of this is stored together in one place. I think that almost everyone wants to be able to tell a story like this, right? They want to be able to justify why their model made what predictions it's made, makes what predictions it's made. And doing this is possible in sort of a traditional sense without a feature store with REST endpoint deployment. It's just really hard. You just have to stitch together a million different components to get this end-to-end story. At this conference, there's been a lot of talk about model interpretability, right? It's a hot topic in machine learning. And that's great if you can look deep into your neural net and see, sort of given what, why does it, given X, why does it produce Y? But this takes that story to the next level, right? It says, what was the data involved? We all know that data is the key component, right? What predictions, what features went into the model for your neural net that you now have some understanding of how it works to make those predictions? With just the understanding of, the model, you're lacking a critical component, right? What is the data? What predictions were actually made, when, by whom? That's what the system gives you. So now I see another question in the chat here. The distribution that we see here is of the target variable. In that case, the model distribution, I believe, would be built in future than the time and the model is predicted. I'm referring to the distribution comparison between model training. Give me just a moment to make sure I understand this question here. I'm not sure if I actually 100% understand the question, but I'm going to just explain what's happening in this graph as best as I can. In the blue here, we have of the features that this trained model, that this deployment table has in it, like of the columns this table has, right? What did the distribution of features look like when the model was trained? Now, how are we able to give you that information, right? In this deployed model, in this TWiML regression table, we have associated with it this run ID. As part of run ID, as stored and logged in Mlflow, is this database transaction ID. We can then go back in time and see the distribution of features when the model was trained. In terms of creating the orange here, right? What features has the deployed model actually seen? We just get that directly from that deployed model table. And so we have the distribution of features when the model was trained, the distribution of features of the deployed model. These are two static points in time, right? A year ago when it was trained and today, but you could also imagine tracking this over time, right? We could have this, this orange side be a month ago, a week ago, today, etc. Yes, it's the distribution of each feature that makes sense. Exactly. That's exactly what's going on. So at this point, that pretty much concludes our hands-on demonstration. Oh, I never started the Spark session. That pretty much concludes our hands-on demonstration of Splice Machine. What I'm going to do now is bring in two of my colleagues, Ben and Sergio. Ben and Sergio are real experts on this system, and they might be able to answer some of those more in-depth questions, such about the optimizer that were asked before. So Sam and Jose, I'm not exactly sure the process to get Ben and Sergio on here. Fantastic. So before I pass it over to them, I'm just going to return to my slides. Who would I be without them? And just sort of give a few closing words before we finally open it up to questions. So what's next, right? I just showed you Splice Machine as it exists today. It's going to look a little different at the end of Q1. We have big plans for Splice Machine Feature Store version 2, which is launching in March. The first is the updated user interface, which I showed you before. The second is a question that was asked earlier. We have some APIs to manage backfill and feature pipelines. You're more than welcome to do that yourself with SQL, but we're going to try and make that a little easier for you. And we're going to have some more granular permissions over some of these API functions. You know, we have role-based permissioning built into our system. We're going to give you a lot of flexibility with that role-based permissioning. If you want to continue with Splice Machine, which I hope that you all will, these clusters that you guys are all on right now are going to end at the end of this talk in about an hour. If you want to keep going with Splice Machine, we definitely invite you to do so. You can sign up for a free trial, which will put you back on a cluster very similar to what you were just on, or a personal demo with myself at Splice Machine, or my email here, which is jploshnik@splicemachine. In terms of the code itself, we are more than happy to share that with you. It's in a GitHub repo. Happy to hand it over. Just reach out and we can talk about getting that to you. In terms of actually really taking the next step, you're impressed by what you see, you want to move on with Splice Machine. You can purchase a cluster sort of per hour in the standard way through the AWS marketplace. That'd be a great way to maybe test it out. But the way that most of our clients purchase Splice Machine is you license our software and we put it sort of on your AWS, Azure, GCP, or on-premises cluster. And so reach out and we can get you started and get that set up. So now I will move on to questions. Thank you so much. Feel free to just ask away, and I'll direct them to myself or Sergio or Ben as appropriate. Ben, you want to go ahead and answer this question here?
Sure, I'm just reading it. Well, Sergio, why don't you answer the original question while I read this slightly longer one?
The original question being the one about distribution. I think it was already answered, right? The distribution that we were displaying was each feature's distribution as it was compared to the training set. So we calculate the distribution on each of the features that was used for the training, and we compare that to the distribution seen in the model evaluations in each of the features now that the model is deployed.
Cool. Okay, and so this is cool. This is a good question. So this is a question about using REST APIs, having one endpoint to have multiple models hosted at the same time for blue-green deployments or for canary testing, things like that. It's a great question. At the moment, we only support deploying one model to a particular table at a time. So if you wanted to have blue-green deployment, you would have, for example, 2 tables, and you could insert into one or both, or based on some probability that you choose. In the future, a coming feature is being able to have 2 models deployed to a particular table and being able to direct that based off of a probability that you decide.
And Sergio, back at the beginning, there was a question about the optimizer. I thought best left to you.
Oh, yes. So okay, a little bit about our database optimizer. So as other analytic databases, we collect statistics on the tables, and you do that through the analyze. You might have seen it in our sample code. So with that statistical information about the data in each table, the database takes any query and it uses those statistics to figure out a plan. So this is, just like any other cost-based optimizer in a database. The difference in Splice Machine is that our cost-based optimizer is cognizant of the fact that it has two engines. It has a key value store engine, which is the underlying HBase engine that we use for the quick operations, right? So if we see a query, if the optimizer sees a query that's a point in time, I'm sorry, an individual primary key lookup, or it's a individual index path with a few joins, but it's all indexed such that we're accessing very few rows, it recognizes that and uses the HBase engine to resolve it. That makes that kind of query very performant for high concurrency situations. So our database supports the high concurrency related to feature serving in real time based on that functionality. On the other hand, if the query is a complex query, like you saw the one we built with the bunch of left joins with the temporal conditions to find the right features to build the feature sets for training, that's an analytic query that's going against potentially massive amounts of data. Our optimizer recognizes that. It recognizes the complex joins, the large amounts of data involved, and chooses our OLAP engine to resolve the query. Our OLAP engine under the covers is Spark. So based on that, we automatically direct to the query to the right engine. And it also allows us to do something else very interesting, which is scale each of those engines independently. So you can scale the number of OLTP units addressing the high concurrency fast workloads related to feature serving separately from scaling the number of Spark executors and the number of pods associated to Spark for the analytics side. So based on what your feature store workload looks like, whether it's lots of online activity and even at different times of the month or different times of the day, you can use scaling up and down of the different resources to enable both the training side and the serving side.
Thanks, Sergio. Then I'll take a look at Miguel's question here. Is it possible to have alerts for the model drift use case? I don't believe that's a functionality we currently have. That's something that maybe we should consider adding in the future. But I really want to stress, making that model drift story, right? Making the graphs that I showed you before, the skills necessary to do so is a relatively simple SQL query, right? And so for you to set up, a query that runs every so often and have an alert associated with that would be very easy to do the way our system is designed.
Just to add a little bit to that, we actually have Grafana natively implemented into the system, and we expose that to the user, and you can create alerts based on SQL queries in Grafana that can hook into any of the Grafana outposts that you want. There was one other question, Sergio, you could take if you want, that was about the external table access, just kind of going into how we do external tables in more detail.
Right. So I believe the question was around, what happens, we have this automatic history keeping mechanism that, if you're generating new feature values every second, it's going to get pretty big pretty fast. And yes, it will get pretty big pretty fast. But our database allows you to offload data, right, into external storage. And the way you do that in Splice Machine is actually quite simple. You create something we call an external table, and this is a create table, just like any create table, except it has the word external, it has a location for it, and it has a format. So you can store in text, in Parquet, in ORC, and I believe we also support Avro. And you can store it in blob storage, in S3, in Google, in any cloud storage, or even in your own distributed HDFS if you want to do that on-prem. So that allows you to offload large sets of data, even partition it and put it into this external table. And the way you actually feed it from one table to the other is a simple insert select. So this is where we say the database functionality actually enhances the abilities of the feature store, because we could take the history of the feature set that is live online and just grab, a month at a time and push it off to external storage, or an hour at a time, whatever the granularity of your partitioning off to external is in your design.
Okay, so we do have you know, some time left, and this was left intentionally. My hope is that you guys, you know, are using the system and have some, you know, have some questions sort of in the hands-on experience. Now would be a great time if you want to know, you know, how do you do X, how do you do Y, what is the way in which this particular function works. You know, to the extent to which you guys are following along at home, now would be a great time for us to help you with that process in any way we can. Sergio?
I'm not the best person to answer that question, but so it's talking about the standard rates for licensing costs. We do. I'm not completely aware of what the current pricing model is, but on-prem we sell in different modes, right? We sell by cluster node. In the cloud, we sell by hour, by vCPU hour. So you know, contact us, and I'm sure we'll come up with it with the appropriate pricing mechanism for you that works for you.
You guys are on a bit of a hot seat, I see, waiting for questions. I would suggest if you want to allow folks to kind of continue working through the demo, we're going to keep this Zoom room open through to the next workshop. You guys can go off camera and maybe monitor the chat. And if you see someone, you know, popping up with a question, feel free to pop on and answer it. No need to stay in the spotlight for the next hour, unless you want to. Totally up to you.
For that,
There is another question that came in from my buddy Gavin.
yeah, that's a really good question. What we have right now, it's a lot of Python and Scala. It's definitely true some Java as well, because it's a lot of Spark-based execution. For the APIs, we have a Python SDK, a REST API, and coming soon is a SQL-based API in terms of actually interacting with the feature store, not using SQL. At the moment, no. In terms of the feature store API, you can definitely write Clojure code, but it would be interacting with the REST API directly. Cool. So what type of support do you have for media data, images, sound, and video? Cool. That's a great question. In our database, we support all the standard SQL data types as well as both clobs and blobs. And you can create any features that are of type clob and blob and store those just like any other feature. And you can access them with SQL or using the native Spark data source or through any of the feature store APIs.
That's great to hear, Thomas. If you have any additional questions, you know, definitely let us know. Are we hiring? The answer is yes. we would love to have you. We have our postings on the website, and definitely reach out to any of us individually if you would like any more information. And I guess I should mention the hiring. We're also growing quickly, so more talent is definitely in demand. Indeed, we were remote long before 2020. We have members of our organization ranging from the Silicon Valley to Spain and everywhere in between. So, we would love to, remote first 100%. In terms of the new release, I think I would just mention in March, as I mentioned, we're adding some new functionality, which includes, I think, primarily the user interface, but also some additional APIs with our feature store. And so I guess the reason is, we're always improving. And I should mention, we have the feedback part. We added the feedback to the Jupyter notebooks for a reason. If there's some functionality that you would like to add or you think is necessary, we definitely invite you to put that in. We would love your feedback. The product is dynamic. We're always improving. Yes, that's a great question. I think I was a little bit imprecise. There is the features. There is the database, which is directly tied to both the feature store and the machine learning deployment, system. What I meant to say is that you can use the feature store without the model deployment system, and you can use the model deployment system without the feature store. That's what I meant when I made the modularity point at the very beginning.
The question for people who couldn't see that question is, you say there are 3 components that are modular and separable, hybrid DB, feature store, ML platform, but the feature store seems to be intimately tied to your database, or is that not the case? That's what Jack was just answering.
Yes, so it is indeed intimately tied to the database. Yes, it's a great question. So in the closing moments here, I think it would be great to invite our CEO, Monty, on. Jose and Amari, if you guys could bring him on, I think that would be great.
Thank you. I think you guys can see me and hear me. Is that right? Great. Well, Jack, thank you very much. Ben and Sergio, appreciate you joining up and answering all the hard questions. There was a question about our future release and what's the thinking behind it, and beyond the feature store, perhaps it makes sense to talk a little bit about that. The user interface that Jack flashed in the beginning is one small piece of an entirely new look and feel that Splice Machine is going to launch. It's a UX that is extremely streamlined and providing a much better experience for all aspects of the Splice Machine solution. We have customers using the solution just to power real-time applications without machine learning in it. We have customers using it to do real-time AI in the midst of sort of factory settings and being able to predict outages in real operation technology arenas. We have folks using it for applications in healthcare, and we just wanted to make a much better experience. So that's really exciting for us. We have new database features that are coming in that enhance the database across many different dimensions on the OLTP side, as well as on the OLAP side. Being able to incorporate dashboards and alerts as a first-class object in the user experience is really important to us. There were a couple of questions about that. How can we monitor for skew? How can we monitor for model drift and other elements? We didn't demonstrate that today, and we're really excited about having a first-class dashboard capability where users will be able to create any arbitrary dashboards. For those of you who are familiar with Grafana, Grafana is particularly good at building dashboards of temporally changing data. and being able to zoom into different regions of time as things change, and to create online alerts. And those alerts can, be both on dashboards as well as through other channels, like you would expect, like PagerDuty types of alerts and things like that, Slack integration, all those kinds of things. So the ability to not just have the data foundation in a feature store, the modeling foundation to create the predictive models that you saw Jack demonstrate, and you actually deployed yourself today, but also being able to have a full observability platform. And I think that's going to be a big major add to the next version of the system. We've also incorporated a fully integrated NiFi capability. We didn't talk about our connectivity capabilities today in any details, but we alluded to being able to get to data sources of all different kinds, both batch and streaming. We talked a little bit about external tables that are first-class tables that are on other sources that we can join together with our tables. But the new user experience will have a first-class section for building pipelines in NiFi and being able to, essentially create those arbitrary both streaming and batch connections to other external sources out there. And we've even made some improvements to our Spark integration, where, as you saw today, we were manipulating data frames all over the place. We've really enhanced the performance of our native Spark data source. And that native Spark data source allows us to expose the executors that our database is actually using to the user in the notebooks. That's kind of what we were using all through the feature store when we were returning data frames. We didn't have to materialize the data out of the database. Those were lazy evaluated via Spark, but we've also incorporated in the newest version of the system Spark structured streaming, and to create something called a native sync in Spark structured streaming. And this is one line of code that allows Spark structured streaming to essentially use the Splice Machine data store as a sync, and it will maintain the high watermarks of streaming. And we could, even in that scenario, I think we've been able to prove something on the order of 100,000 tags, which are temporal data sources in a streaming scenario in industrial frameworks per node, which means you can do 1 million per second with 10 nodes of ingestion. So those are just some glimpses of the future for us in March, and really excited about that. And should anyone on the call today who's had a little hands-on taste of Splice Machine want to be part of the beta testing for that version, also please contact Jack. He'll be coordinating some of that as well. And we just want to thank everybody for their participation. We took a little bit of a chance today. We noticed that many people were just doing demos during these workshops. Our team here thought it would be really cool if everyone can actually get their own little sandbox. And we said that, hey, we're Kubernetes orchestrated. We can automate the entire thing real time in front of everybody. And we all thought, well, that's a little risky, but you guys pulled it off. So proud of you. So thank you, everybody, for attending, and we'll stick around for more questions.
We do have 2 new questions here. The first is about using AI for the A/B testing of the new UX features. I'm not sure. I think the answer is yes. Monty, do you want to elaborate?
Yeah, that's our intention. Our intention, actually, we're going to, Ben said very quickly earlier about the new feature coming that will allow us to essentially have multiple models be deployed and to be able to perform A/B testing across those models with an experimental test bed. That's something we'll use ourselves, and every aspect of our user experience is going to launch into significant A/B testing. Whether we'll be using AI, all the time and machine learning all the time, I'm not sure that that's our fundamental goal. Our fundamental goal is to really just test our interfaces with good experimental structures. So we'll do a little bit of that. We'll also be using significant tracking in our application of the journeys people are taking through the application. And one of the things that Jack is implementing himself as a data scientist is the ability for us to identify people as they come into our platform and try to infer based on how they were introduced to Splice Machine or how they self-declared, which is much easier. What is the job that they need to get done? Well, are they a data scientist who are going to be mostly doing models? Are they a data engineer that are going to be building mostly pipelines? Are they an application developer that's going to be serving models in an application? And making sure that their first experience on Splice Machine through a trial is going through a journey that's really applicable to them. It's such a robust and comprehensive platform. If you take a Java developer who just wants to build an application and throw them into a Jupyter notebook and give them a TensorFlow model to try, it's a mismatch. And so and vice versa. So we're going to be able to use our own models to infer what's the next best journey to help guide a user along using chatbots and other kinds of capabilities in our user experience. So I hope that answers that question. I guess there's a question about Prometheus. I'm going to take that one, guys, if you don't mind. And we're all on the call together, and we were very careful not to step on each other and answer questions. But now we've got a bunch of us on here, so Jack, you can delegate questions. I'll just take that one first. Prometheus is actually in the system. We didn't show you the cloud management user experience today, where you can create, every one of you who's online created a free trial. If you were a paying customer of the service or using the same stack on premises, you might have many databases that you're managing and workspaces for machine learning. Behind the scenes, every one of those are fully instrumented. And so today, we use Prometheus to manage very low-level log metrics behind the scenes of the clusters themselves. Those are basically Kubernetes and Java-based metrics that are coming in real time, and we graph that in Grafana out there. So that's what we use Prometheus for under the covers. But with regard to, I'll say, user-level data, or data that you're modeling about, not system-level data, we have a full temporal database capability. The underlying OLTP system in Splice Machine is, as many of you already know and Jack mentioned earlier, the row-based storage and OLTP compute engine is based on HBase. And HBase is, for example, the engine that's powering one of the most popular open source temporal databases, which is OpenTSDB. We have very similar functions where you can essentially be doing temporal operations on a first-class basis using our SQL layer. And in fact, the feature store does precisely that. When Jack demonstrated and you executed the get training set from view, the query that was done, and I think we showed you the SQL query, was a fairly complex set of joins that were executing interval logic there. And essentially, and very much aligned to one of the questions that was asked in the chat, what if there was lots of different timestamps coming from different cadences and all these different feature sets? The feature store is actually using interval logic in SQL with very fast execution times in order to do point-in-time consistency for the feature store's training set execution. So net, the crisp answer is Prometheus is in the system and connected to Grafana for activity metrics at the system level, but now Grafana is available for temporal operations at first-class SQL level in Splice Machine as well.
And we've got a great question about model size. You want to answer?
Yeah, sure. So actually, it depends what you mean by size. I don't know if you meant like size of the physical model artifact or the size of the amount of data being put into the model at a particular time. Okay, great. So in terms of, okay, there's 3 answers. So in terms of training the model, because it's all distributed in Spark, increasing the amount of data that the model is training on, obviously it makes it take longer, but we handle that completely fine. We'll scale out with the data. In terms of serving the model, we actually, when you deploy the model in the database, like you saw, it actually gets faster with the more rows you put in, obviously to a threshold, but we batch the records that you insert into the table and we transform them in batch. So that actually gets faster. In terms of the size of the model, I don't think that we've done comprehensive testing on the physical size of the artifact. I think the biggest one that we can deploy in the database is 2 gigabytes. I think, I'm not 100% sure, but you can store them externally and then deploy them as pods in Kubernetes to any size. But in terms of the performance degradation, we actually cache the model in memory once it's used on every server. So the first record that you insert may take a little bit longer to load that model, and then every subsequent record will be extremely fast because the model will be available in memory.
We have a computer vision deployment that's quite large. Yes, Ben?
Yeah, so that model is deployed and hosted in the Kubernetes environment the way that Jack explained. And those records are actually also persisted in the database through an asynchronous connection.
Sergio, do you want to?
Sure. So the question is, for a feature engineering process scenario where the processing can be computationally expensive, is it possible to distribute the processing using Spark process cluster that is used by the feature store? And the answer is yes. Actually, there's actually 2 ways of doing that, which are interesting, right? One is just through SQL, right? And that automatically, because it's an analytic query and our optimizer will select the Spark executors to run that. One way is just running the SQL and letting the database use the Spark executors that are provisioned for that purpose. A different one that's also possible is spawning a Spark cluster separately and using our native Spark data source to use that particular Spark cluster to do the job. So from that perspective, you can create any size Spark cluster you want on the fly to run a feature engineering process, run the engineering process, insert the data or upsert the data back into the feature set, all of that from any Spark cluster you want.
In addition to that, there's a new feature in the new version of the system I think is germane to talk about from that question about resource allocation. Resource allocation is really important in general. Jack earlier said we are a hybrid database engine under the feature store that keeps analytical queries isolated from the transactional queries, and that is true. And those are different JVMs that use different resources. They have a small amount of contention at the IO level when they're both accessing the same IO, but the computation is separate. In addition to that, in our OLAP engines, we have a new feature in the database level called application server queues. We're elevating that into the user experience on the cloud service. So available today is this idea that you can allocate Spark executors to different queues and assign roles to various people, including systems like the feature store. And each of the way the database deals with this is as you issue SQL to the database through any connection, it knows the initiator of that statement. That statement is then forwarded to an appropriate application server queue, and that application server queue has a certain number of Spark executors associated with it that is dedicated to that queue and scheduled within that queue. And so you can start now to isolate different workloads, both from different applications like the feature store, or even if there are multiple organizations in an insurance company, let's say the feature store is being used by folks in marketing, folks in underwriting, folks in risk, folks in claims, and you might want to give different queues to those different organizations and give them different levels of resources according to the organization. So that's another way of doing resource allocation in the underlying data systems that's available today in our base platform and actually being brought up to the, so you'd have to get some of our help to use it today on the cloud service, but it's actually being brought up to be self-service in the cloud service and the new UX in March. All right, maybe it makes sense for the team now to shut off our cameras and go into background process. We'll stick around and certainly answer questions if people are still playing with the system for a while. Again, thank you very much for the great questions and thumbs up to the team. And you guys did a great job. So signing off. Thank you, everybody.
All right, I'm just going to hop on quickly to say that our next workshop will be starting up in, is that, ooh, my math is real bad here. Top of the hour. So come back for that. If you have questions or if you're still working through the Splice Machine demo, keep working and we'll be around for, or the team will be around for your questions. You can just add them to the chat. But see you back soon for the next workshop if you're through.
Hey, Gavin, I just want to make sure I understand your question correctly. You're asking if if the application server queues are using Kafka? Okay, great. So the answer to that is no. It is based on Yarn Kubernetes allocation.
Another quick question, Gavin, just to repeat it. So if I want to make language bindings outside of Python, I have to use the REST interface for now. That is the case. We're working on APIs, native APIs in the future. The first one would be SQL. So what is the fidelity of the REST and the APIs? I do not have a full answer to that. I will check and get back to you. The second question, which is what is the fidelity of the REST APIs?
That's great, Gavin. Much of this is open source, so we definitely welcome your contributions.
If it helps with the performance, we're using Fast API under the hood, but I don't. I mean, maybe if you asked slightly differently, I'd be able to answer it in some more specifics. But our API is written in Fast API.
Yeah, so Sam mentioned that we can allow anyone to ask their questions in real time, with their voice and the chat on. We are more than happy to let you do that. I think the best way would just be to post in the chat if that's something you're interested in, asking a question in person.
Hey, Jack.
Hey there.
Hey, this is Gavin. Yeah, I'm still thinking about the system as a whole and where the seams are, because you guys are using different technologies, and the devil's usually in the details of these seams between connecting them. Like with the story that you guys told us about the optimizer and the routing and these things. Yeah, I'm mostly curious about some of the design choices. Were there any particular design choices that were noteworthy that you would want to share or that come up?
Yeah, I'd be happy to pass it over to Sergio. He knows a little more about the details there than I do.
So, I'd say our primary design choice and the essence of how we're going about the feature store is how we're implementing the feature set and the history keeping mechanism. So I think the motivation was we are a hybrid HTAP database, and we've been so from the very start. And as the machine learning industry has been evolving over the last few years, feature stores suddenly became an important thing, and we realized quickly that most feature store implementations are using two engines, right? They're using a key value store for the quick feature serving capabilities, and a different engine. In most cases, we see Hive, or we see or data warehousing technologies, something that's highly parallel, right, and capable of large queries. So our database was a natural fit for that. So we started building an API around it to build the feature sets. And when we did that, we said, well, it makes sense for us to automatically take care of the history keeping mechanism. So we designed the trigger generation mechanism that builds that history keeping mechanism. That makes sense?
Yeah, certainly.
And with that, we started building the other aspects around it, right? I guess the other motivating factor is in order to keep the feature retrieval quick. That's why we decided to split the data into two tables, where we're keeping the current values always as a primary key lookup that allows us to, under the covers, use the key value store that implements our data storage mechanism that's HBase, and take advantage of the very fast key lookups that HBase provides. So that enables feature retrieval, and at the same time, by keeping history on the other table, it allows us to do the large analytics. Our database takes because when we built the query generation mechanism from the metadata that retrieves training sets. And uses all those left outer joins that you saw, and the temporal joins, that naturally takes advantage within our optimizer of the OLAP engine and runs in Spark. The other advantage, and it's just a natural advantage of our database in this sense, is that given that the feature retrieval is an OLTP workload, and training set generation is naturally an OLAP workload, the resources used for one and the other are naturally separated and naturally scalable separately because of the hybrid database that we've built.
Nice. So data at rest is always in the database, right? They're ginormous files for pulling down different data sets and so on and so forth. And files have been sort of the currency, right? When you want to give your data to the world or anyone else, right? You give them a ginormous file and say, go get it. In this case, the database is first, as opposed to files.
Correct. Yeah. I mean, yes. If that's the question, yes. Definitely the database is our our primary access mechanism for training, as an example, right? We're getting the training sets directly from the database by resolving those queries to produce the point in time feature vectors. The other thing to think about in a feature store, right, is sourcing, right? The sourcing of data, which is going to come, like you said, potentially from files. So there's still that ability to take batch files and process them either through Spark or through SQL mechanisms to feed the feature sets, right? That's one way of doing it. Because we're running on a Kubernetes platform where we have I wouldn't say a full Hadoop stack, but some of the Hadoop elements in it, including Kafka. We enable also direct streaming, right? Either through our Kafka cluster or through some other Kafka cluster or some other queuing mechanism cluster to do structured streaming. And like Monty mentioned, what we've done for that is we've built the structured streaming sink. What that allows you to do is do all of everything you can do in Kafka from a structured streaming perspective to process the pipeline as it's coming in, and then directly feed that into a feature set that will then from then on do everything we've been talking about, the history keeping and all the other aspects of it. So that enables the streaming inputs into the platform. And finally, the real-time event processing can also be done directly on the database because it's an OLTP database and it can scale the OLTP engine separately. You can actually have applications, let's say something driving some website functionality. You could have that application running the tables that run the transactions for that application be running on Splice Machine and have triggers that use those new transaction inserts or new transaction updates to then do some calculation to feed a feature set. So from that perspective, you can use triggers to actually have full real-time model evaluations.
Very
So anyway,
cool.
those are the few elements that come to mind from a design choices perspective.
Yeah, cool. Again, this is my first time really looking at the product. So I'm just tinkering and asking questions.
That's cool. And we're glad to do a more in-depth conversation with you if you want to.
Cool, thanks. I think that's all I have for intelligent questions or quasi-intelligent questions. Everything else.
Those are all great questions. So.
Thanks for answering them and your patience. Appreciate it.